Okay, so hello everyone. In this video, we will be seeing regarding how Edge Shard is running on a full agent stack, local agent stack, and hope you all had reached or seen the previous videos in which we had talked regarding how Quadrant Edge is working best when using vector size. Okay, so, how the thing is that your agent's entire memory, semantic search, keyword search, compression, multi-agent isolation, running from one folder on your laptop, no server, no internet needed after setup. So, let's build it. Now, see, what in this video will be starting is the name vectors and plus the hybrid search and plus the TurboQuant. So basically all the things on your single device. Okay. So a complete AI agent memory system that runs entirely on your laptop. No cloud, no API keys, no servers, just you, Quadrant, and a local embedding model. Okay. So how it will be going is, so basically first of all, what is an edge shard? Okay, so think of it as a tiny database that lives in a folder on your computer. Instead of sending data to a cloud server, everything is stored on search locally. Edge means it runs on the edge of the network, your laptop or a phone, not in a data center. Okay, so basically this will help you running your entire database, okay, without any network or without any API keys. So that would be much helpful when going to your own device and not using any network. Okay, so basic, and then what are named vectors? Okay, so each piece of a data gets one vector with named vectors. Each piece of data can have multiple vectors, each with a name. Like the you can see on the screen the example, like dense so captures the meaning of the text, but what is sparse captures the exact keywords in the text. Okay, so that's how the hybrid search works and the turbo quant. Okay, and third thing is what is RRF, reciprocal rank fusion. When we combine results from dense and sparse search, we need a fair way to merge them. Okay, RRF is a simple algorithm. It looks at the rank of each result in both lists and produces a combined score. Items that rank high in both searches get boosted to the top. Also, in previous videos, you had seen that according to the scores which are displayed, okay, and according to the query. So basically it aligns the score with the query, and according to that the highest number of score comes at the top, and that is follow up by decreasing the scores. So that's how these things work. Okay, so yeah, the thing is by the end of this video, hybrid search over dense and sparse vectors on the same point, compressed with product quantization, isolated by agent and session, with surgical vector edits and full portability, all local. So let's go. Now I will be showing you one image regarding how the things work. Okay, one second, just it is loading. And so here you can see that how data points when comes at dense and when comes at sparse, okay, connected to the payload, and according to that the ranked result list is created for dense and for sparse, and once both are there, we combine of both of them, and with the help of RRF, okay, we create a single rank list with a score displayed. Okay, so when the user query is generated or the user sends a input, according to that semantic search is gone, and according to that the scores are generated from the database. Like, yeah, this is the most relevant uh, data which we got according to the user's query, and according to that it is showed on the screen as an output, that by decreasing the score like something, and yeah, so the top will be at the most score, and going towards the down, the least score would be at the bottom. So that's how it works. And here you can see that, yeah, two arrows branch to two labeled capsules, one with a smooth gradient. So below, two small rank result list icons are there, and uh, we can see that, yeah, merge via a funnel into one final ranked list labeled RRF. Okay, a small tag below the point card reads payload with key value dots. So that's how it works. And coming to the next image, so here also, one second, yeah, so here also we can see that how the total of 1536 bytes, okay, is shifted like to 96 bytes, okay, with the help of dense and sparse vectors combining to get a rank list of both for a dense and for a sparse, and once combined through RRF creates a final rank list, and through that the 1536 is minimized to 96, okay, so that's a 16x decrease, and that's how Qdrant is booming in this, okay. So let's start with the working. Okay, so first of all, we are installing the dependencies, which are Qdrant client and fast embed. Okay, once those are done, let's just start with that. One second. Yeah. So once it is running, yeah, so I think it's done. And coming towards the next part, so that's initialize the IH chart and local models. Okay, so basically how it works, see, we will be giving in an database path which is integrated in the Qdrant client, and once we will be running that, okay, with the help of loading models, and yeah, let's run this. Okay, so here what we will be getting is one second, yeah, so one second, it is running, and here we can see that the loading embedding models are run, are completely going on correctly, and the download is complete, and fetching the 5 files on that. And what's the dense model is a BGE small, that is of 384 dimensions, okay, and that's how it runs. And the sparse model is splayed PP. So quick peek at what the models produce is dense vector for hello Qdrant is here, and sparse vector for hello Qdrant is 12 non-zero entries with 30,000 vocabulary terms. So everything is ready, no cloud, no GPU, 100% running locally, okay. And then comes the create the collection with named vectors, okay. So going to that, now we create the collection. Okay, so two name vectors are there, dense, okay, so that will be a fixed length, and sparse will be with a variable length, okay. Purpose of what is semantic meaning and keyword matching, okay. See, so the original vector which is currently in the image is of 1536 bytes, and after PQ, so each vector would be like 96 bytes, okay. So for a million memories, 1.5 GB is compressed to 92 MB. So hope if you are a developer, okay, so you know that yeah, 1.5 GB of RAM using to 92 MB of RAM using, okay, so that's a lot difference when running on local device, okay, without any internet. So that creates a very great difference, and that's a great thing we are using Qdrant, okay. So now generating the collection name like agent hybrid memory, and then comes with the client collection exists, okay. Then the vector config where the dense, okay, the dense is starting, more vector parameters, the size is 384 dimensions, the model is BGE small, okay. Now the quantization configs, and then coming to the sparse vectors, okay. And once the sparse vector is also done, the sparse vector parameters, and then comes the that part, okay, the edge optimization and all. So once we will be running this, here you can see that yeah, the collection agent hybrid memory created dense vector at 384 dimensions and sparse vector split compatible, okay. Now let's verify and inspect the collection. So once I will run this, and here you can see that collection details are there, name, status, points count, and indexed vectors, okay. So as running this, the name is agent hybrid memory, status is green, points count and indexed vectors, okay. Then the vector configurations and the sparse vector configurations, okay. So that's how we initialized the edge chart and created the collection name. Now let's come to the next part, that is let's verify it, okay. I think it's done also. And yeah, coming to step 3, create payload indexes for multi-agent isolation, okay. So before adding data, we set up a payload indexes, okay. So how it will be running is see, the client, we created the payload index, okay, given the file name as agent id, and according to that it runs. And once coming to the next part, so that is another file name which is session id, and then comes the timestamp, okay. So that's how it will be working. And once we will be running this, here you can see that yeah, the index are created on agent id, index created on session id, and index created on timestamp, okay. So payload indexes are ready, filtering will be fast even with millions of memories, okay. So step 4 is populate the agent's memory, okay. So now let's give our agent some memories. We will create a realistic scenario, okay. Okay, so I will running this, and here you can see that the embed text is takes a text string and runs both dense and sparse vectors. This is the core function that turns text into searchable vectors, okay. And here you can see that the helper function is defined and the usage is done, okay. So the dense vectors and sparse vectors are embedded text, and once you will be writing your text here, okay. Then comes with the agent's memory, okay. So here we had created a file in which all the details are there, and yeah, so the id starting with 1 fixed a critical null pointer exception in the payment processing module. Agent id is agent coder, session id is debug session 1, timestamp is this, and according to that we had created this database, okay. And I think this is initialized. We will run this, and here you can see that the embedded memory till 1 to 10 all are fixed. So here we can see the description, and here's the memory, and all the 10 memories stored in the edge shard, okay. So what we did till now is we created the edge shard, we initialized it, we created here you can see, one second, yeah, so here you can see that yeah, we also created the payload index. And once all the things are done, here you can see that yeah, each point has one dense vector plus one sparse vector plus metadata payload, okay. So all the things are there. So now let's verify. So we are checking the data, and yeah, so once I will run this, okay, and here you can see that the retrieved point is yeah, the payload, the agent coder, session id is debug session 1, category is bug fix, and all the things are stored. Dense vector, the 384 dimensions part, the sparse vector 96 non-zero entries. So all the collection now has 10 points stored successfully, and here you can see that, okay. Now comes the next part, that is hybrid search in action, okay. How it works is, so basically the query comes how to fix database connection issues, dense search, then finds the semantic similar memories, okay, then sparse search, and then comes the RRF fusion, merges both results list by rank positions, okay, that we had seen in this image, okay. Yeah, here you can see that the ranked list for dense and for sparse both are combined, and one single rank list is confirmed with the use of RRF, okay. So how hybrid search works is, so basically here you can see that yeah, how to fix database connection issues, searching as agent coder, okay. Now here you can see that the scores are there, the 1 0.66 0.50, and according to that it will be giving what we can say, the most relevant matching outputs, okay. And then comes the agent research plus session isolation, okay. Once it's running, yeah, I will be showing you, yeah. So the quantization techniques for edge deployment, okay. And here also you can see that the scores are there, 0.833, 0.750, 0.583. So according to that, most relevant searches according to the user query, okay, according to the query which then goes for semantic searching. And once the semantics are there, it will be matching from the database, and according to that it will be giving outputs with the most relevant ones at the top, okay. Now dense versus the sparse versus hybrid, okay. We had run till now the dense vector, the sparse vector, also we had see the hybrid part, okay. Now let's compare all the three. Now here you can see that yeah, comparing search strategies for reducing memory usage in application, okay. So the dense only will be semantic meaning itself, okay. The sparse only will be for the keyword matching, and the hybrid part, okay, dense plus sparse fused with RRF, okay. So dense is working at semantic meaning, sparse is working at keyword matching, and hybrid is at RRF, okay, combining both. So notice hybrid combines the strength of both. Dense finds the semantics, sparse catches the keywords, and hybrid means merges both for the most relevant results. Okay. Next comes the dynamic named vector mechanics. Okay. So how it will be working is remove a named vector from specific points. Okay. So here you can see that the before removal, point one vectors are dense and sparse. Okay. But after removal, okay, so we are removing a named vector. So here we can see that the dense part is there, as semantic part is there. Sparse is keyword matching, so it will be missing, as we had removed a named vector is removed. Okay. Next is updating the named vector. Okay. So how it works is before update, point one dense vectors are this. Okay. And after updating, so here are the points. So the dense vector has changed, but the payload remains untouched. Okay. Now re-add a previously removed name vector. So we'll be adding those name vectors which are previously removed. So here we can see that before we can see that the shard is missing. Okay, sparse vector is missing. Now it is come. Okay, so point one is fully restored with both named vectors. Okay, now the step 7 is bulk vector operations. We are going in a bulk part. Okay, so that's why databases are right now booming, and Qdrant is at the peak for that. Okay, so simulating bulk model upgrade for agents coder memories. Here we can see that they are re-embedded 0.12345 from the database, and the bulk update is complete. Okay, now comes the edge migration. Okay, now we will be running this. So at the output you can see that they are closed current edge shard connections, edge shard backed up with the source and with the backup. Okay, and here also we can see that the agent edge memory folder is created and all the things are in it. Okay, and here's the sample data, the readme part and all the things, but this is not necessary. And then we will be verifying the backup works. Okay, now here we can see that the backup verification successful, and it run completely, and collection agent shards and search on works. Okay, so everything runs properly. Then comes the migration approach. Okay, so the snapshot code is there. Once it will be running, all the things are here. Okay, so on the source device connecting to the Qdrant, so here's the source client, create a snapshot of the collection and then download the snapshot file. Okay, so that's how it works. And then once we will be running this, reopen the original edge shard. So successfully closed existing Qdrant client instance before reopening, reconnected to original edge shard. Okay, collection already has 10 points, so the points which are there in the database are retrieved properly. Okay, now comes the advanced payload filtering patterns. Okay, now here we can see that first of all the query is what went wrong with the system, and then once it analyzes that, okay, and according to that it will be giving output. So here we can see that they are bug fix and optimization. Okay, so the time range filter would be all the things from the data set are retrieved, and see here also we can see the timestamp, and also exclusion filters are also there. Okay, so everything except the agent coder are here. So complete payload isolation, each agent sees only what it should. Next comes the memory sizing. Okay, so will this fit on my device? Okay, so here we can see that the memories part, the RAM, the disk, and the RAM with output as PQ. Okay, so the dense vector as PQ 16x part, sparse vector, and the payload. Okay, so what are the key takeaways is without TurboQuant, 1 million memories is 1656 MB of RAMs. Okay, so that's a 1.5 GB of RAM, and with TurboQuant it is just a 282 MB. Okay, so that's a great difference. I think that's an 8x less part. Okay, so 83% less RAM is used, and it helps a lot. Okay, a laptop with 8 GB RAM can comfortably hold 1 million agent memories. Okay, so that's how it works. And once it's done, so yeah, uncomment the lines above, and yeah, so the capstone summary would be edge shard, the name vectors, TurboQuant, hybrid search, isolation, vector operations, bulk migration, and memory sizing. Okay, so with the help of Qdrant, combining TurboQuant with the help with Qdrant. Okay, this creates a very huge difference when running on your own device. Okay, so also here you can see that without TurboQuant how the results are. Okay, and with the help of TurboQuant how results are. Okay, so that matters using Qdrant with TurboQuant and running on your own device. so database would be retrieved very properly. Okay, so that's the whole part when using TurboQuant and all. Once I will show you, I think there's another thing I have to show regarding I think it's an image 7. Okay, one second, it will be loading. So I will show you regarding, yeah. So here you can see that memories RAM with PQ and RAM without PQ. Okay, so 1000 memories would be 250 KB, but without it is 1 MB. Okay, so when coming to 1 lakh, that's 25 MB, that's 100 MB. Okay, so the 75, what we can say is one fourth part is there. Okay, and when comes to 1 million, so 250 MB and 1 GB. Okay, so that creates a vast difference. Okay, so that's the whole thing when running the part, and the one edge shard full local agent stack is running properly on your device without internet, with no API keys, no servers, just Qdrant and your local embedding models for dense vector and sparse vector, giving the results and combining that with RRF. What RRF is, we discussed, and also I will show you again. When we combine results from dense and sparse vector search, we need a fair way to merge them. Okay, so RRF is a simple algorithm. It looks at the rank at each result in both result lists and produces a combined score. Items that rank high in both searches get boosted to the top. So that's how it works. Okay, and hope you learn new things in this video. So like, comment, share and subscribe to HiDevs. Hope we would meet in the next video with more new things. Okay, so thank you and keep